This is the screencast for section 1.4, example 2, composition of functions. We are going to compose one function into another. I think you have experience with this mostly in Algebra 2, where we take the input of one function and plug another function in to that input. Sounds complicated. Hopefully I'm going to straighten a few things out. I'm going to use some fancy colors. So in example 2, f of x, the purple function, equals e to the x. G of x, the green function, equals the square root of x. The instructions say find f of g, which means take g and plug it into the input of f, and find g of f, so take f and plug it into the input of g, and verify that those functions are not the same. Well, let's find them first. So f of g of x means take the f function and plug in g of x for its input. Well, the f function is e to the x. X stands for the f function's input. But I'm not going to use x anymore. I'm going to use the whole g function, square root of x. So e to the square root of x is f of g of x. Now the other way around, g of f of x means I'm going to start out with the g function and into its input plug f of x. The g function is the square root of x, but instead of plugging in x, we want g of f of x. So I'm going to plug in the f of x function e to the x. So first of all, these don't even look the same. E to the square root of x and the square root of e to the x algebraically don't look the same. Numerically, I could even plug in the number 1. Oh, by the way, e, we're going to learn more about e in chapter 3, where it comes from, how it helps us, what role it has on the planet in mathematics. But for the meantime, e has a value 2.71828, etc. So let's try and just plug in, let's see, we'll do e, so second natural log, which is right next to your 4 key, to the square root of, let's plug in 1. That has the value of e, because e to the, well, square root of 1 is 1, so e to the 1 is e. That second function is asking for the square root of e to the, we're going to plug in 1 again, first, so when I plug in 1 to either function, I do not get the same output. So numerically, I've verified that those functions are not the same. And we could graph in y1 f of g of x and then y2 g of f of x to see that they graph to be two different functions, and graphically show that they are also not the same. The now try problem for example 2 is exercise 15. Find f of g of x and g of f of x, and then it also says state the domain of each. So f of g of x, so I'm going to make f the blue function, g the pink function. F is 3x plus 2. But instead of using x for the input, I'm going to use the g function for the input, x minus 1. So that would be f of g of x. Then if I wanted to make g of f of x, I would start with the g function, x minus 1, but instead of x minus 1, instead of x as the input, we're going to use the whole f function as the input, so 3x plus 2. So we have the two composition functions created. Now we need to state the domain of each. The domain of composition functions is very difficult to understand. This is a simple example. In example 3, we'll get into more complicated ones. These two functions both have domain and range all real numbers. They're lines. So when I take the g function, start on the inside, work your way out. When I take the g function and I plug a number into it, I will get out all real numbers. Then it just so happens that f's function, I can also input all those real numbers that came out of g. So the composition function still has domain, all real numbers. Same with g of f of x. When I plug any number into f, all real numbers will come out of f. Then all those real numbers can easily get plugged back into g because g's domain is all real numbers. So the domain of this composition function is also negative infinity to infinity. Again, for a clearer understanding, and which will definitely come from an example where the domain is not all real numbers, for more complicated examples, see example 3.